All right. Hello, everyone. This is Jorge Nicho from Southwest Research. Welcome to the MoveIt Community Meeting 2016. This is the second year that we do this, and we have a number of awesome presentations for you. So let's go ahead and get started. So hopefully, right now we have about 32 people signed up for attending the meeting. Hopefully more will join. But here's the agenda for today. We'll have Dave Coleman start up with the latest developments in MoveIt, and then we'll talk about SBPL by Dr. Maxim and Andrew Dornbush. And then we'll move up to the FCL Collision Library by Dr. Dinesh. And after that, we'll have Delph winning Amazon Picking Challenge from by Mukunda Baratisha. Hopefully I pronounced that correctly. We'll follow it up with Michael Ferguson, and we'll talk about MoveIt and how we use it in robotics. And at the end of the presentation, we'll have a Q&A with the original MoveIt developer and founder, Dr. Ioan Sucan. So before we start with the presentations, just a quick remark about how to ask questions. So when the presenter is speaking, you'll be able to ask a question by typing it in the chat window. And then at the end of that presentation, I'll go ahead and ask the question for you. And then during the Q&A, just type your question again on the chat window, and I'll unmute you so you can go ahead and ask the question yourself. All right, with that, I'll go ahead and allow Dave Coleman to speak to us about the recent developments at MoveIt. So I'm going to go ahead and load up his presentation. Just give me a second here. All right, Dave, go ahead.
All right, thank you, Jorge. Can you guys hear me?
Yep,
yes.
We can hear you.
All right, great. So I'm Dave Coleman. I've been helping a lot with the maintenance of MoveIt, and I'm glad that we can have this meeting today to kind of get some more communication on what's been going on and newest features. As you see in the overview here, we're going to go over some new features that we've been working on the past year, as well as other things like code cleanup coverage, the kinetic release, general documentation, and community. And then one thing I'm excited about particularly is talking about future goals of this project. So to get started, we'll start with the high-level GUIs. We've had lots of contributions from different people. So throughout this presentation, you'll see mentions of the GitHub username of whoever took the lead on adding this feature. So for example, there's now a stop button in RViz. So while your robot's executing on real hardware, you can stop it and it'll preempt the action. And then there's interactive markers that will automatically update to the current state of your robot so that you can replan quickly. In the trajectory display, Robert has added the ability to interrupt a trajectory being executed and add a new one. Brett Hems has added the ability in the GUI to set the velocity scaling and acceleration scaling. And what this means is that your robot has max velocity and max accelerations in its URDF and its YAML files. You can actually scale that between 0 and 1 to change speed effectively. And finally, some other buttons have changed. In the Simple Assistant, we've seen a new screen added for author information, as well as a command line interface to make it easier to change things quickly, and other GUI tweaks to improve the usability of it. In the Move Group class, we've actually renamed the interface, the C++ interface, to be more clarified from the Move Group node, two separate concepts. So you'll see that deprecated in Kinetic, and moving forward in future releases, we'll totally remove the old version. By the way, a lot of these features that we're mentioning today, almost all of them, a lot of work has been put into it to make sure there's backwards compatibility. So for example, we've added the execute trajectory action to eventually replace the execute trajectory service, but that they both still exist. And for now, you'll just get a warning if you haven't switched yet. But this new action is good because it allows us to stop the trajectory being executed once it started. So this goes along with the stop button GUI piece in RViz. And to use this new feature, you'll need to either update your MoveIt config package or rerun the setup assistant. In addition, we have a new capability for applying a planning scene. This is great. Michael added this, and it allows us to actually block until a new planning scene collision object has been added and then continue. And this prevents needing arbitrary sleeps and having uncertainties of if it took or not. On the planner front, we have revamped the chomp planner. So it's still an experimental phase, but it's building again. Previously, it wasn't catkinized. So we've had some progress in that. And then eventually there's a PR in the works for Stomp to get that working again with MoveIt. Still, of course, OMPL is our default planner. And there's recently been added some work on accessing the optimization objectives. In the main project, they have the ability to optimize for certain things, such as distance from a collision. And we've added hooks to use that more in MoveIt itself. And we've have discussions going on today about SBPL and sorry about that. Looks like the slides are acting up. We have discussions today on getting SBPL working with MoveIt again. There's a fork where it works, so we'll have more talk about that later today from Dr. Likhachev and Andrew. These slides are really acting up. All right. Another new feature is the benchmarking suite has completely changed. Previously, we had two packages called MoveIt ROS Benchmarking and MoveIt ROS Benchmarking GUI. The GUI is now gone because it was never finished. It had lots of seg faults. It had a warning telling users to be careful if they actually try to use it. And so we've switched over and tried to combine forces with the OMPL project at the Kavaki Lab, Rice University. We're using the same suite they use. They have this pretty impressive web GUI. So now in MoveIt, if you want to benchmark planners or other features of MoveIt, it'll output your results to configuration files that you upload to this Planner Arena website, and you can compare it against other planning works. And as Mark Moll's pointing out here, Ryan Luna actually did do the initial work for this. I grabbed these names based on the GitHub pull requests, but the original version of this code was definitely Ryan. So hopefully we'll see more work with that. There's a tutorial on this in the MoveIt tutorials website. In terms of safety, we have a great new feature. Previously, there was nothing to check if the first state of your trajectory that you're trying to execute varied greatly from the current state of the robot. So you'd have this big discontinuity and this big jump in acceleration and like the robot going from a current state to something very far away. Now it'll actually cancel a trajectory if it's not within a certain threshold of joint values. So you can adjust how close you want it to be. But this is a great improvement from MoveIt. Additionally, we have 3 new controllers for fake controlling. So if you're not actually connected to hardware, there's different modes you might want to use a fake controller. Robert's added being able to smoothly interpolate or just showing via points or the last point. So it's immediately jumping to it. Those are all in the MoveIt plugins package. And then lastly, I'm excited about this. We have better ROS control integration. Previously, it was kind of ambiguous how to connect ROS control to MoveIt. You'd use the simple controller manager. This gives us a better interface, allows us to switch controllers using the same features that ROS control has overlapping with MoveIt. So that's been a great contribution. I hope to see more work with that in the future. On the kinematics front, we have consolidated the different kinematic solvers in MoveIt into a single package called MoveIt Kinematics. This won't break anything because they're just plugins that loaded through plugin lib, or shouldn't break anything. And we additionally have a new kinematic solver, Levenberg Marquois, that has this table here shows the results of a particular robot benchmark, and it showed that this Levenberg version can outperform our default KDL solver, which is Newton-Raphson, solving more % of the time in less time. I think your results will probably vary depending on what kind of kinematic hardware you have. And of course, you see that the IK fast solver still outperforms outperforms the % solved. So I encourage people to look at that, benchmark that, and if you have results to share, please contribute it back to the community. Another exciting development is the kinematic base, is the base class of all our kinematic solvers in MoveIt. And we now have hooks, thanks to Jorge and other people at Ross Industrial, to support multiple redundant solutions. So not only can you request for a particular pose one solution, but you can get a whole slew of them. You can specify what discretization you want those at to get different redundancies. And finally, we have upcoming changes to the kinematic plugins, thanks to John and myself, to improve the speed of loading multiple kinematic solvers if you have a lot of threads or a lot of different move groups, and we'll just be passing the robot model into that. So looking forward to that. That PR is already in progress. On the collision checking front, we had huge improvement for large meshes. Levi at Ross Industrial saw a 1000x speed improvement for his benchmarks of 10,000 triangle count meshes with FCL. So that's really exciting. It just involves caching the objects. There's other improvements from Ross Industrial guys in the pipeline, but hasn't been merged directly in. And hopefully today we'll hear more from the FCL folks about their improvements that we can maybe move back into the MoveIt project itself. And we also now have catkinized again the collision distance field plugin, which is necessary for, I think I have this right, for Chomp. And that's also building again. For dynamics side, nothing major. We're still mostly kinematic solver library, but we, as mentioned earlier, have hooks for changing the acceleration scaling factor and the ability to copy from your joint state ROS messages into a robot state and move it, the velocity and effort. Pretty minor changes, but, and there's also lots of other small changes that I just wanted to shout out.
You're responding now, right?
I'm hearing microphone noise from someone out there, if you don't mind muting that. So you see the small list of other changes going on. So exciting progress. On test coverage front, we have our first integration test, thanks to Robert, including a new robot for testing, the FANUC M10. Various speed improvements, tests in geometric shapes, that's exciting. Until recently, our CI, our continuous integration, had been falling apart. So we now have full integration testing for Indigo, Jade, and Kinetic. We had to use Dockers because Travis doesn't support Ubuntu 16.04 yet. And we have a repo that if you're using a MoveIt-based project, you could easily use our same CI that's optimized for the MoveIt build. It's called MoveIt CI. I encourage you to check it out. It does a lot of pre-caching so that we can meet the build times. There's been a lot of code cleanup. Michael has done a lot of ROS-lint and catkin-lint work to just make sure our CMake lists are correct. We had a big repo consolidation that we advertised a lot. And that was exciting because now it's a lot less friction in getting changes and finding where the code belongs. Little upgrades like Eigen3, which is always seemingly causing problems. And just this week, we code formatted the entire code base of MoveIt. So now it's all exactly the same type. And if you submit a pull request, we have tests that will ensure that it's to format standards. So we encourage you to check out our documentation on the website on how to run claim format on your pull request to make sure it's the correct format. It basically follows the raw CP style guidelines. For the Kinetic release, we've switched to C++11. We're using shared pointers. Lots of progress there. Thank you for everyone who helped with that. Kinetic is currently in shadow fixed. We have not yet finished supporting, I believe it's Wiley that's holding us back for a previous Ubuntu version, but that's coming out. It should be fixed soon. Robert's working on a fix for that. We now have names, so that'll hopefully help with ABI changes. More information on that is on the website. For documentation, we have a unified tutorials website now called MoveIt Tutorials. We've taken all the different Sphinx-based tutorials throughout our repos and put it in this one package. It has the PR2 tutorials in there also. But if you see changes or fixes you want to do, please, we encourage you to work on that. We have a page based on all the different plugins. There's like, I believe 7 or a number of plugins in MoveIt, and this talks about the different ones. And we've done a lot of documentation of procedures for how to do pull requests and maintainers and so forth. If you're interested in installing FCL, OMPL, MongoDB, other projects from source, we now have instructions in our install page for how to build those with MoveIt in Catkin from source. And we have lots of other small changes to ensure that our documentation stays up to date, like automated checks for dead links. Oh, and lastly, we've announced this week through our maintainer meetings that we want to switch to ROS answers for our user questions rather than mailing lists. We want to keep the mailing list just for announcements and really high-level discussions. If you have new MoveIt work you want to show off or share, that's a good place for the mailing list. In terms of community, we just had a World MoveIt Day. I think it was a pretty good success with 65 pull requests. We had several locations, including Fetch and Examia. and lots of progress that day. We started doing monthly maintainer meetings, although more semi-monthly, every other month. And the meeting minutes from those you can find on a new discourse group for MoveIt developers. And in terms of growth, you can see on this chart that we've continued to have a pretty steady growth. We're up to over 1,000 users as of yesterday, since January 2013. So that's exciting to see that we've just had nice casual growth upward. We have consolidated our maintainers and added some new ones since our last community meeting last year, including Robert, Michael, Isaac, I think Ian, Gil, Jorge, Christian, Martin. They're all fairly new to the project in the past year, I believe. So I'm excited to have them all involved. They've been helping out a ton. Thank you so much. And again, thank you for our original founders of this project, Sasha and Ioan, etc., for their great leadership in creating this project and getting it to where it is today. I'm going to skip this slide for time. And in the future, short-term goals is we've been discussing fixing the default planner in OMPL so that we have better performance. I think currently K-piece is the default, and it's causing a lot of problems in planning times and reliable solutions. So hopefully we'll see that fixed soon, maybe switching back to RRT Connect. We'd like to see better tutorial cleanup for new users. I think based on the feedback I've gotten from students in my lab, it's still kind of confusing how to start from scratch with learning MoveIt. So I'd love to see a community effort in fixing those up. Again, updating the planner interfaces. I think a grass planning is something still missing in MoveIt. We have a really basic default grass planner, but I wouldn't really consider it a real grass planner. So I'd like to see us kind of converge on a more decent one that will be default. And of course, individual labs can customize it with their own raw services to their own grass planner. So if you have one that you think it would be appropriate for this and you like to open source and see moved into the ROS planning organization, that would be great. Let's start that discussion. We've had a long-standing bug with our trajectory parameterization in terms of continuous accelerations. So I'd like to see that improved. I know Fetch Robotics has mentioned they have a version that could solve this problem for us, but a small improvement that would really help the overall project. I think Python support has issues with our current MoveIt commander. We could look into using a package like MoveIt Python, switching to that, which is a more pure-based Python. So I'd like to discuss that more. And finally, FCL, there's been hints there's lots of improvements we could do to get faster speeds. That is like the biggest bottleneck in motion planning. So if we could see those integrated, such as the work at Ross Industrial, that'd be great. Long-term reactive control is something that I think this framework really is lacking. So the ability to not only do kinematic plans, but also then do changing modes between controllers, impedance, force, visual servoing, that really would close the loop in the quality and the reliability of manipulation that we can achieve. I talked about this in my ROSCON talk last year if you want more information. And finally, better Cartesian planners, such as Descartes. So that's all I have. I want to encourage everyone here today to please help out in contributing code, bug fixes, documentation. We've done a lot of work on this link you see here on explaining how to do that and trying to making it easier, reducing the friction and helping. So that's the current state of MoveIt as of 2016. Thank you all for being here today. And now onward to our next presenter.
So Dave, there is a question here from Sean.
Yes.
Edwards.
Sure. He asked, how do you enable fake controllers? They work with the MoveIt controller manager, just like a regular controller. So you have to load one up. Most people load up the MoveIt simple controller manager to just use the ROS actions. But in this case, I believe instead of using the MoveIt simple controller, you just switch to one of the ones. But I think that'd be a better question for Robert, who created those, and for the documentation on the mailing list.
Thanks for answering that. All right, looks like there aren't any more questions here. So I had a quick question for you, if you don't mind.
Sure.
So you mentioned that there was now a feature that allows to check if the start state is close to the current state of the robot. And there's a way to set the tolerance for how far those are from each other. So if they're different, how does it handle that particular situation?
If they're different, it will just cancel the request.
Okay.
And I think it'll ask you to replan. I'm not sure if MoveIt will automatically replan or not currently. I think you might, like, if you're using RBizGUI, you'll have to press plan again.
Okay, great. All right, well, I think that's that. That was pretty great presentation. Thank you for that, Dave. And,
Thank you, Jorge.
now we'll move on to the next presenter. So, Dr. Maxim and Andrew, I'm gonna load your presentation. Just give me a second here.
Hey, Jorge, you're switching the presentation, right?
Yes, just give me a second.
All right, cool. Yeah, first of all, thanks for having us. And second of all, I also wanted to commend you guys on having it online. I just love the fact that I don't have to travel for this anywhere else, and we can just do it right from the office. That's terrific. That's it. So my name is Max Likhachev, and also Andrew Dornbush will be the presenter, and he is a research engineer in my lab, and he's the one that basically worked on a lot on SBPL, and particularly connecting it to MoveIt. So I'll try to talk for a few minutes to give a general overview of the library, and then I'll shut up and I'll let Andrew talk about how in particular it connects to MoveIt. Let's see it. Right, so that's the outline. So the overview of SBPL is basically based on a heuristic search-based planning library. So it contains a number of heuristic search algorithms ranging from a standard A-star search to anytime incremental version, and some of the latest additions which we have a multi-heuristic A-star search. It is a standalone library on its own. So it can actually be compiled and used on the Linux and Windows and so on. And in terms of integrating it in ROS and in particular in MoveIt, I'll let Andrew talk about that a little bit later. You can check it out at sbpl.net/software, the site for it. And the library itself was used on a number of different platforms, pretty much kind of anything in terms of robotics that you can think of: ground, aerial manipulation, mobile manipulation, and humanoid. Let's see. All right, so as a heuristic search library, it's basically the idea is that you're trying to generate a systematic graph representation of the planning problem. So it's you're looking for a very systematic representation and then searching that graph with a heuristic search, and of course, given the high dimensionality of the planning problems, it usually generates this graph representation on the fly, so it dynamically generates the state. So it's pretty much never generates the states up front. So in terms of pros and cons, I'm sure you guys, most of you know, but on the positive sides, you have a pretty good cost minimization. You have quite a consistent motions because it doesn't involve any randomization to it, and it has a kind of a natural way to incorporate the discrete aspects of the planning problem. So if you have questions about which arm to use, to what to kind of to grasp, which handle to grasp, and things like that, all those discrete things, then it's pretty naturally folded into it. On the negative side, a lot depends on the quality of the heuristic function that you design, and clearly if it has deep local minimum, then it will slow down the search dramatically. So it's important to design good heuristic functions, and that's domain dependent kind of thinking. And then the coming up with a compact graph representation for a particular planning problem is, of course, is important. So the way it's split is that basically you have the domain dependent and domain independent parts to it. The graph searches algorithm like A-star, anytime A-star, and the multi-heuristic A-star, all of those are domain independent. And then there is three kind of main functions that are domain dependent, which is the graph construction, so the actual generation of the successes for a given state, the cost function, and the heuristic functions. So meaning that the estimates of cost to goal. So those are the domain dependent, and the library itself is exactly split along that line, so that you have basically a number of graph searches that are sitting there, and there is also a number of graph representations that are already pre-built, and more can be added, and any one of them can use any graph searches, and any graph searches can be combined with any of those planning problems. Now, so the right, and I already mentioned that it's a kind of memory allocated on the fly. It's important for high-dimensional problems, and those two things, the graph searches and the actual planning problems, that completely decoupled and they just communicate with each other via state ideas. So the kind of the core library is this kind of the smaller box, and then on top of it you have the overall planning module, and that's outside of the library itself, but rather this is the where it comes in, the integration into ROS and MoveIt and so on, and that's the thing that sits over it and handles things like updating the pose and the goal updates, and the calling replan when necessary, and so on and so on. So on that, I guess Andrew will talk about that a little bit. In terms of the last thing on my side is in terms of the latest additions, as I said, multi-heuristic A-star was added, one of the latest algorithms that we developed that basically supports a number of different heuristic functions. So, for example, it's useful in the cases where, let's say, planning for a humanoid, where there's a number of different ways how you can decompose the problem and compute the low-dimensional heuristics for the base, for the arm, and so on, and then you feed them into a graph search. And then one other thing that is coming up is the experience graphs. That's one of my students did a thesis on this, and that will allow to feed in the demonstrations into the planner and have those demonstrations guide the search, and also to let the search learn from the experiences. So those are the links. I will let Andrew talk, and then I think after Andrew talks, that's when we're going to go answer the questions, if you guys are okay with that. So I'll let Andrew talk, and then, just keep on asking questions, and then after that, we'll answer those questions. Andrew, go ahead.
Yeah, do you have to reload new slides?
Andrew, yeah.
Oh, yeah.
A second to upload your slides.
I got the mouse.
Yeah, here's the mouse.
Thanks. All right, cool. Good morning, everyone. This is Andrew Dornbush, and I'm going to be talking about something that I'm just starting to call the search-based motion planning library. So where this will differ from SBPL is it'll have consistent interfaces for typical robot motion planning problems, whereas SBPL is inherently domain-dependent and doesn't include a lot of the graph representations that we've developed over the years. And then, of course, I'll discuss the integration with that into MoveIt. So if you take anything from my portion of the talk, it's that the source code is available on GitHub. They're currently under my personal GitHub accounts, aside from a few which are under the primary SBPL GitHub. The project in general is split into two portions. There's a core planning library, which has very minimal dependencies on MoveIt. It doesn't require the MoveIt runtime at all to function, so you can incorporate it into other projects. It also includes our in-house collision checker that we also wrote. And then there's a separate repository for a series of plugins that use the planning core and can be loaded into MoveIt via plugin lib. So this will include a separate plugin for running our planners, another plugin for using our alternative collision checker, and then anyone who's worked in motion planning has probably figured out that not one algorithm solves every problem, so we have a simple meta plugin which can simultaneously load any number of planning plugins that you have available in your workspace.
Somebody has a microphone unmuted and typing, so if you guys can just mute it, that would be great.
No, I'm sorry, that was
me. All right. So I'm going to skip over most of the history, but I just want to say that the original ARM planning work was started by Benjamin Cohen from the University of Pennsylvania, And since then, we've integrated his ARM planner on a number of robots, but most of them have been limited to the 7 degree of freedom ARM configuration, and we've had to develop custom solutions, such as for this 6 degree of freedom KUKA that you see in the bottom left. Also in that picture, you can't see it, but there's a 5 degree of freedom base, which also uses a custom SBPL solution as well. As of last fall, we started work on a generic ARM planner that has first-class integration with MoveIt. So the core SBPL planner supports what we've been calling the manipulation lattice. And this is your dense representation of the robot state space, where you have a discrete variable corresponding to each joint variable that you have in your robot model. So it also supports several ways of making the graph search more efficient. So you can design the motion primitives to use any joints you want, and you can explicitly develop like the length of these motions to speed up your search problem. And it also correctly handles discretization of the joint space and ways of dealing with discretization errors and hitting goal tolerances. Primarily, this lattice was developed to handle only 6-DOF goalpost constraints, but we have some experimental features on doing other types of constraints supported by MoveIt, such as joint goal constraints. The primary heuristic that's used in it is an obstacle-based heuristic. So you have a voxelized representation of the world, and we solve the planning problem in a lower 3-dimensional space, and we use that as a heuristic function, so you don't get stuck in local minima around obstacles. As far as support with SBPL goes right now, we currently support planning with the ARA star algorithm, as well as a lazy variant, which is able to postpone collision checks, which can speed up the search pretty dramatically for a lot of problems. We have experimental support for multi-heuristic A star as well. So as I said, there's some experimental features that have been recently developed. So we have support for joint goals and different lattice representations, which may be more suited to different planning algorithms or different planning problems. On the limited horizon, we're looking into doing experience graph support that can support arbitrary robot models pretty well. We also want to be able to use different cost functions. These are similar to the optimization objectives in OMPL. And then there's also several other kind of more planning domain specific algorithms that we have that reason about the state space that you're planning in. And we'd like to get some of those lattices in the planner as well. And then lastly, support for more generic state spaces, such as having a 3 degree of freedom constraint or a 6 degree of freedom constraint. We'd like to support those as well so we can target mobile manipulation planning problems. So I'm going to digress a little from the planner and give a short little segment on the collision checker we made. So for many of our planning domains, we've opted to use an approximate model, which can have several orders of magnitude in speed up over using the full mesh collision checking that's provided by FCL. So this isn't a replacement for FCL, because there are certainly problems where doing mesh collision checking is worthwhile. But for several problems, using an approximate model can dramatically speed up the search. So in this collision checker, we blanket the robot with spheres, and it automatically creates a sphere hierarchy, which we can then check against a voxelized representation of the world. So every one of your collision checks becomes a very simple distance lookup, and that can be extremely efficient. We can voxelize octomaps out of the box. We also have voxelization routines for collision objects, pretty much any shape supported by geometric shapes. And you can also voxelize the links of your robot that you're not planning with to gain additional efficiency. And then for any of your links that aren't voxelized, you can cover those in spheres and do explicit collision checks between those. There's also very experimental support for auto-generating the spheres, but that part's definitely future work. So everything before this slide was on the core SBPL, which doesn't require MoveIt at all. The MoveIt Planner's SBPL package will provide the extensions. All those plugins are loadable by plugin lib, so you can just swap OMPL for SBPL and give it a try. So I encourage everyone that has a robot model to go ahead and download the package and test it out. Let me know what the most requested features are, because we certainly don't have the amount of support that the OMPL planners have. But it's very close, and I'd like to hear what features are most requested from users. That's all I got. I'm open for questions.
All right, so I think there are a number of questions in here, so I'll just go over them. The first one were consistent motions that were mentioned earlier at the beginning by me. By consistent motions, what I meant is the for similar start and goal pairs, you're pretty much getting a similar motions, the planned motions, and that's due to the fact that there is no randomization in the process. So you're getting pretty much the same motions for the same type of queries, and those also typically close to being cost minimal, so you kind of get a solution that is a reasonable solution in terms of explaining what you're getting back. So that's with respect to the consistency. In terms of the pros and cons of SBPL over OMPL, also, first of all, let me just start by saying that in general, I would love to see the SBPL somehow incorporated under the OMPL, but I think we had a long time ago discussions about that. I mean, it's not that straightforward due to the very different type of structures that we're using, and the kind of the fact that we're going SBPL, we're going for explicitly discrete representations and supporting kind of discrete problems whenever there are discrete problems. Anyway, the pros and cons. I think if you have kind of a time to spend on getting your planner fitted towards the planning problem that you have, then if you can put that time, then you can generate a planner using SBPL that will give you solutions, as I said, that are very consistent and usually relatively close to cost minimal. But the negatives is the fact that you do have to spend time and kind of thinking about the planning problem that you have and figuring out what are the informative heuristics that can guide the search well. So there's it's a trade-off between how much time you want to spend it, and if you do want to invest time into it, then I think it's worth it. You're getting a solution that are explainable, you're getting solutions that are consistent, and you're basically kind of more reliable in terms of what you anticipate to have. But then, if you're kind of going for the faster solutions, then OPL is a great solution for that. Let's see. The next question was, the joint state goals. So before I get, let Andrew answer it, I also wanted to mention about that. I think from the very beginning for us in my lab, there was always kind of interest in terms of planning to a particular grasp pose, so to a particular either 3 degree of freedom or 6 degree of freedom pose, as opposed to the full robot configuration. And that was basically the driving factor for the initial search that we defined, because rather than trying to run IK and figuring out which is the full goal configuration, you let the planner figure out how to get there, as long as it's in a position where it can grasp. I'll let Andrew add to it if you want to add something.
That's pretty consistent with what I would have said. Our primary use case was coming up with grasp poses, and also the obstacle avoidance is in the workspace. So the heuristic that we're using has a deficiency when it comes to hitting joint goals exactly. So the joint space planner that we have now it works with the obstacle based heuristic, but it works better if you just use straight up Euclidean distance in joint space. I think it's definitely an interest of mine to try using a multi-heuristic approach where we use the Euclidean distance as like the primary heuristic and then have an additional heuristic that provides the obstacle avoidance information.
Right. So I think the next question is regarding the why not use FCL with sphere, the hierarchy.
I think the practical answer is we've had our collision checker for 5-6 years by now. So we've been using it, the same one, for a long time. I'm not sure, someone could maybe correct me, but we do our collision checks mainly against a distance transform on a voxelized representation, so it's not straight up sphere versus sphere collision checks. So we get a lot of efficiency out of just doing that. But someone can correct me if that's available in FCL.
Okay. And then there is autosphere generation, experimental autosphere generation. MoveIt, I don't know if you had a chance to play with that or not.
I've not.
Okay.
Okay.
There was one more question. Okay. Are there plans to support control-based planners as well? Control-based planners meaning, are we talking about like where the lattices or the motion primitives that basically correspond to controllers, running controllers? If that's the question, I think at some point, yes, but not in the near-term future, because I think that requires us to think about the right representation there as well.
All right. Well, excellent. Thank you for such a great presentation. Good to see that there's another planner available as part of the MoveIt library. And with that, we'll go ahead and go to the next speaker. So it's going to be Dr. Dinesh and Jia Pan with updates to the FCL, the collision library. So I'm going to go ahead and upload your presentation.
Hi, this is Dinesh, Manocha at UNC. Can you also make sure Jia Pan is here, because this is actually a lot of Jia's work and he'll present it. Is he also been, can you put him on? He joined the audience right now.
Okay, just give me a sec.
This was the work that Jia started when he was way back at Crashner at UNC with folks at Willow. And so he probably has more insights than I do. So I'll let Jia present it. Jia, are you there?
He's
An audience, so can you put him
in
on?
the audience. For some reason, I'm not able to unmute him. Can you have him call us?
He's actually in Hong Kong. It's middle of the night, so. That's why I sent you an email before the meeting started that could you give him you sent an invitation as an audience, not as a presenter. So that got
confused. I sent him an email so that he can log in as a presenter.
Okay. Let me just type for a second. If not, then I'll present. But that's why I was resolving this with you before.
Oh, there he is. Okay. He's hey, Jia.
Oh yeah, I'm here. Yeah.
Excellent, great. Welcome. So we were about to. Well, the mic is yours now. So go ahead and tell us about FCL.
Oh, okay. So this is just a brief update about an introduction about the FCL, and so I mean just some like a very brief history. So basically FCL is just a very small project starting in 2011 when I was in Robotics, and originally it was designed for the like motion planning stack in ROS. But now, of course, it is a standalone library, so it's not bundled with ROS anymore. And so basically, the goal is that we want to perform very efficient motion planning in a human environment with very cluttered and moving obstacles. And so we want to make sure that we can handle the collisions for the data from the 3D sensors. And because they are very large and also very dense. So basically is that we hope that we can build some collision library which can provide some real-time computation support for the fast online reactive grasping and motion plannings. So the main reason why we want to start a new like collision detection library is because at that time, of course, there were many different implementations and libraries for the collision checking, like ODE, PQP, Bullet, and Rapid. And but when we want to use them, and we found that there was one main problem. So for example, most of them only implement a subset of the functions which is required by the robotics applications. And even though some of them support a large part of functions and are highly optimized, but that's still like not convenient. And because, for example, if I want to use a collision checking and some distance checking, distance computation, and usually the user need to link with a large number of different libraries, and you need to convert different data structures like among different libraries. So this is not convenient. So this is the main motivation that why we want to start a new collision library for that. So after some investigation, at least in Uruguay, we found that okay, so here are a list of functions which is required by robotics applications. The first is that you need to represent objects by different representations. Now, for example, if the data is from the CAD models, then it's in mesh. If the data is for the robot links, but then sometimes for the efficiency, you want to represent the links in some very primitive geometric shapes like sphere or like cylinder and so on and so forth. And if the data is for the sensor measured obstacles, then probably it will be in point clouds or in some data structure like Octomap. And the second function is that okay, given two objects with maybe different representations, and we want to perform some Boolean collision checking between them, and also some particularly for some like grasping or motion planning applications, you want to return where the collision happens, and you want to sometimes you may also want to know what is the normal vector at the point where collision happens. So you also need to have the collision positions and the normal as the return. And sometimes also you need to want to compute some real valued distance between objects. For example, it can be used as some heuristics for the motion planning. And when you are computing the distance, usually you may want also to return the closest point pairs. And another useful like function is how to compute how two objects if they already like collide in simulation. So what is the penetration depth between them? So basically, penetration depth will give you the minimum translation distance required to separate two objects. So basically, by that time, we think okay, all these four functions will be the most important for the robotics applications, and we want to include all of them in one library, so that you don't need to switch between different libraries to use different things. FCL, the features is that okay, so from the beginning it's designed as a fully templated code in C++, and also it's designed to be easily extendable, and so that you can add new algorithms and new approaches if you want. And the current features include like some low-level collision checkings between the different objects with different representations, and also it can compute the distance between different objects, and it can also provide quite efficient and different implementations of the n-body collisions or n-body distance computations. And also it can have some experimental code for the continuous collision detection. Basically is that, okay, given wind trajectory of the robot, so whether the trajectory collide with obstacles or not. And also it can deal with the Octomap, so that you can perform the collision checking between the sensor data and the robot. Something else is that, okay, there are some, actually in the FCR, there are some low-level acceleration routines which can help you to do very efficient computation, especially when the scenario changes slowly. So basically, this means that FCR, if you go to the low-level details, it can allow you to leverage the temporal relationships in the motion. But of course, these kind of low-level acceleration is not open for users. But if you want to use them, actually you can use that anyway. So to use some low-level accelerations there. This is some like some basic ideas about how to represent the objects. So first representation is of course a mesh. We basically just use the bounding volume hierarchy to provide acceleration for that. Actually, so we have the concept of the bounding volume hierarchy actually has been extended in FCR. It has been used for both for the triangle mesh and also for the point cloud in terms of the octomap. And also, actually, we also use that to perform the collisions between the primitive shapes and the triangle mesh. So the BBH actually is a like basic trick in the basic technology in FCR for acceleration. And the next thing is about the low-level clean checking. And the first is between mesh and or between mesh and the sphere or some like a cylinder and so on. It's based on the bounding volume hierarchy. And also it can similar things is used to for the very efficient distance computation. But of course, in FCR, at least in currently, the distance computation is still much slower than the clean checking. So we are working about how to improve that so that both the distance computation can be a bit more efficient, so that it will be more useful. And we also provide some like collision checking between the primitives. It's basically that we use some GJK or MPR algorithm to provide the collision and to provide the penetration depth information. And this part of code actually requires some more acceleration. Yeah, and so we have some ideas about that, but it's still difficult to make it. I mean, how to say that? So I think we will spend some more time on that, so that the primitives can be more efficient. So and for the octomap, so basically we also use some techniques similar to BVH to accelerate the collision checking and also the distance computation. Yeah, yeah, that's true. So the distance computation also is available for the octomap, like between octomap and or between octomap and another object. For the high level checking, that okay, how can you compute the collisions or distance between n objects very efficiently? So basically, we apply some hierarchical calling technique to accelerate the test. And in the FCR, it's called the collision manager. So actually, in FCR, we have implemented a wide variety of collision managers. For example, you can do the brute force. You can do some ODE style, like an object collision checking, and you can also do some other tricks like the sweep and the prune or interval tree, and or you can even use some like hash or spatial subdivision tricks to accelerate the n object collision checking. Also, like we provided some experimental code for the continuous collision checking. So just as we mentioned before, like given a trajectory of the object or of the robot, we want to find okay, so whether the trajectory collides with the obstacle. If it collides, then we want to find the time when the collision happens, so that we can adjust the trajectory so that it can avoid the collisions. I did some like test on the continuous collision checking, but still, I think this part requires some more acceleration and more like test. So, but of course, it's very useful. It can be used, for example, for the trajectory accommodation, and also it can be used for the sample-based motion planning. Yeah. I think another thing is the penetration depth, which returns the minimum translation required to separate two objects. And this part is if the mesh is closed, then of course it's well defined. But if the mesh is not closed, then the penetration depth could be yet defined. So, and as a result, I think maybe some more research is required to provide a better solution for the like mesh soup or the mesh which is not closed. And because the penetration depth actually is quite important for the grasping or for the like physical based simulation, and it can provide it can help to provide the contact force and or in which direction should two objects be separated. And yeah, and I think that would be, if we can compute very fast and very reliable penetration depths, that will be quite useful. And okay, so this is some like the integration of FCR with the MoveIt. In MoveIt, actually, in motion planning, the collisions are checked by default using the FCR for each robot configuration. And also in the MoveIt, the sensor measurements about the environment are organized as an occupancy map in terms of the octomap, so that you can directly pass that into FCR for the collision queries. So, and actually, you can also directly use FCR to compute the distance from this octomap with robots or with all the other objects. So that's also available. So this, recently there are many like the modifications and additions by other like community, and so for example the SWI they improves MoveIt's implementation of the FCR. So basically in MoveIt the implementation for the FCR is quite simple. So for every collision or distance query, you need to regenerate the FCR object. So the time is like wasting when you regenerate the FCR objects again. So instead, so SWI, they found that you can cache the FCR objects and update the transform when a collision or a distance query was requested. So this can greatly improve the efficiency of the FCR. And the TRI, they are also doing something about how to improve the FCR. Basically, they have got FCR got rid of the boost dependency, and so because of the boost dependency, they also switch the test suite to the Google test framework. So actually, in the beginning, FCR used the Google test framework, but then like because in Willowguard by that time we are using the boost a lot, so that's why we moved to the boost, and now like we are moving back to the Google test framework. And they also want to switch the math from custom written to using the eigen library instead, because this can help to templatize all the code, so that you can use that for the automatic differentiation. So that if you want to use the collisions in recent like deep learning work, then actually so automatic differentiation can help you to compute some gradient and efficiently. So it's good to allow the collisions to provide some gradient. And also like TI is also working on to get the FCR included into Drake, so that they can do some more like fancy like dynamics like computations. Okay, so actually, so I did not work too much with FCR in the past 2 years after I moved to Hong Kong. But I'm still like began to do some modifications and additions on FCR. So because recently I have just began some project about orthodontics, and we found that actually in dentists there are a lot of applications which involve the trajectory optimization, and so because in the dentist we are taking care of the teeth, and the teeth has a very complicated non-convex shapes, and the contact between the teeth is critical for the dentistry, but it's also difficult for the collision checking. So even though this project is not directly related with the robotics, but still like we want to improve the efficiency and the accuracy of the collision checking, and most importantly the penetration depth, so that we can handle the tasks which is required by the orthodontics. And another important thing which is required in the dentist application is that we want to compute the surface areas between the teeth, because this is some important criteria for the dentist. So this one maybe have some potential like applications also in robotics. So yeah, I think hopefully like we will work on like the efficiency and accuracy, and also the contact surface areas in the next like 1 year or 2 years. So that's all. And if there are any problems, I can answer.
Well, thank you so much for that, Ian. We're kind of running short of time, but I think we have time for one question that's been asked there about the continuous collision detection. If I go back to the question, it says, do you see a possibility? This was asked by Michael Gerner from Germany. So the question is, do you see a possibility to do continuous collision detection for articulated chains instead of just CCD for atomic motions of individual rigid bodies?
I think let me just mention there's been a lot of work on this problem. So at least way back many years ago, we had published many papers on doing CCD and articulated models. I guess the question you're asking is, you want the scalability integrated into FCL? Is that the issue here?
No. The question is more in regards to the type of motion that is examined during the collision test. So right now, I think the allowed motion that you can try is that of an interpolated linear motion and some rotation, but robots move differently from that, where you have all these connected links. So the motion of a link that is at the very far end of a chain will not have a motion pattern such as that.
Oh yeah. So it's possible. So actually, like by that time we have considered about the implement that. So basically, is that given a link, I think given a link structure about the robot, then you should be able to compute the continuous collision checking between the link and the object. Yeah. So, but then I mean the difficulty by that time is that we need some like link structure which is like general and also it does not depend on the FCL, so that we can have that the link structure as input and then perform the collision checking. Yeah.
Okay, great.
Let me just add. I think let me just say one more comment. As you said, there have been different. How do you model the interpolating motion? This is always a challenging problem for different situations. One of the work we had done about 12 years ago, at a former postdoc, Stephen Redon, and view the notion of what we define arbitrary in between motion. So I think what boils down to is the fact how you model the motion, and then when you do the primitive test for that particular nonlinear motion that you model, can you do the primitive test very quickly? So if there's a way for you to support those very fast primitive tests for a particular kind of motion you want to do, then you can add that. So not only you specify the motion, but you also specify the very fast primitive test, and that can be incorporated in the FCL infrastructure.
Okay. All right, great. Well, thanks so much for that presentation.
Let me just one minor thing. So one thing, as you can see, we would like to build a bigger community. As you can see, there are a lot of wonderful things you can do on FCL. We're seeing all the great work at Southwest Research Institute and TRI folks doing. Everybody talking about it. So I think it'd be great to have a bigger community and we can build up, because there's a lot of work to be done. And we really invite participation from the community and more stuff.
Excellent. Well, hopefully more people will join those efforts. All right, with that, we'll move on to the next presentation. This is by Mukunda Bharatisha. Hopefully I said that correctly. He's going to talk to us about the winning Amazon picking challenge. Let me go ahead and change the presentation now.
Hello, can you guys hear me?
I can hear you.
Thanks.
All right, mic is yours.
All right. Welcome, everyone. My name is Mukunda. I was a part of the Amazon Picking Challenge winning team this year. And as you can see, some of the results there. But here today, I'm here to talk about how we used MoveIt for the motion planning part of the Amazon Picking Challenge. So this will be what I'll be talking about. So initially, we started off on thinking about different robot setups, and we used the workspace analysis tools from MoveIt, which are quite helpful in analyzing different robot configurations. And in the end, we came up with the choice of this configuration, which had a linear axis that was going in and out of the towards the bin and away from the bin. And here you can see at the end of the slides, there are some commands which are standard available, and it's quite helpful. One thing to watch out is that these reachability analysis results mainly show that what are the possible number of solutions to attain a certain position, but not really how you get there. So you have to be aware of this. And this is a very simple description of our entire software architecture based on the Sense Plan Act paradigm. And the highlighted parts indicate the modules that use MoveIt. Although I will not be exclusively talking about the manipulation planning part, because that would be a completely different or a new presentation actually. I'll only talk about the coarse motion, fine motion, and the I/O part in this presentation. So how we decomposed our motion module was based on taking some inspiration from last year's talk by Dave Coleman about using the MoveIt pick and place pipeline, and we dissected that a little bit and made our own pipeline. And so this was mainly our motion pipeline. We decomposed into coarse motions and fine motions. Coarse motions were mainly done by using sampling-based RRT Connect planning. And fine motions were also using the MoveIt compute Cartesian path motion planning. What we did for speed benefit is that we computed some robot poses, so joint state poses in front of the bins. And then we decided, we planned these trajectories offline and then stored them in a trajectory cache. We would call it trajectory database instead rather than a cache. And then the fine motions were similar to what happens in the planning pipeline or the pick and place pipeline, where you have a linear approach to a certain grasp pose. Of course, the manipulation planning module that I showed in the previous slide actually provided the input as a grasp pose, and then we used that to decompose the coarse motions and the fine motions. And also we used robot state APIs mostly rather than the move group APIs, because these seem to be having no connections directly to the planning scene, because of which we had much more faster executions. For the I/O itself, we actually had to implement, we wanted to implement an event-based I/O because we had a suction gripper. And also we wanted to have, and especially some of the objects had some light features. So for instance, if you turn on the vacuum before you even approach the correct grasp point, then it would start suctioning even before you actually finished your grasp motion. And therefore, we had to create a trajectory tracker using one more async spinner. So we had some implementation issues, which you can actually have a look at when we make the code public on GitHub. And then we eventually managed to implement a gradient descent-based trajectory tracker, using which we successfully were able to control I/O at various event action points while executing a certain trajectory in MoveIt. But hopefully with the new change with the trajectory execution that Dave talked about in the beginning, we may not actually even need this. And then what we did was, these are the implementation details. And also when we used our system, we did not have support for multiple async spinners, which is now fixed in Roskinetic. Some of the lessons learned, these are the interesting parts. So this picture actually shows one of the defining moments for us, basically, where we had reflections due to the lighting in the environment. And then a part of the octomap was, or a part of the point clouds were missing, and then corresponding octomap were missing. And we were strongly relying only on octomap-based collision checking, and we did not include any redundancy. So we ended up actually colliding with the shelf and breaking the gripper. So the fundamental lesson here is include as much redundancy as possible in collision checking. In the end, we actually ended up including bin collision models, because using the whole shelf as a collision model would introduce a lot of errors in terms of approximating the pose of the shelf, because the shelf was pretty long. It was 2 meters long. And then also we included some sanity checks in terms of where a certain trajectory can start and where it shouldn't. And in case a command is sent accidentally to execute such a motion, we would simply notify the coordinator module that this motion cannot be possible. So this was the first of the lessons. This was also an interesting problem. We ran into quite some delays when we were using collision checking for using Octomap. Here, let me see. So while conducting collision checks, the call to a certain collision check was just taking too long. It used to take almost a second. And then we were using the move group get current state API, which we figured at some point that it would lead to, this is a suspicion, so we still need to investigate, but unfortunately we are not able to reproduce the same situation right now because we don't have the robotic system anymore with us. That there was quite some delay in terms of resource starvation that was being caused at the planning scene monitor level. So therefore, we actually decided to use the robot state-based APIs, and using that, we did not have to use the current state from the move group, and we could actually set whatever state we wanted, using which we successfully conducted very fast collision checks. One more thing we learned was the clear Octomap service was not performing very consistently due to the sometimes if the publish rate of the Octomaps are high, then the clear Octomap service would simply not clear the Octomaps. So we ensured that we have a forced clearance by publishing out of range Octomap values, and then calling the clear Octomap service ensured that we always cleared Octomaps. And we also implemented some trajectory stitching. So for instance, when we have these decomposed motion pipeline, custom motion pipeline, then we can create different trajectories. And then the only thing that needs to change when we combine multiple trajectories is the time parameterization. So what we did was we just stripped off all the velocity information from all the trajectories. And then after connecting the joint state trajectories, we just reparameterized it using the IPTP standard time parameterization, and it was just working completely consistently throughout. Although we implemented I/O in our own way for doing event-based I/O, we are thinking strongly about is that the best way to do it? It's still an open question. We all during ROSCON this year, we also had a chat with Mike Ferguson and Ian McMahon. And once our code, so the recommendation was we first index our code and make it available, and then we see how we proceed from there with respect to I/O implementation, general I/O support. Apart from this, we also had some generic lessons. In the behavior design, if we do want to implement interspersed plan and act, which was the idea, so that we could save time and actually conduct the pick and place motions even much faster, there was a lot more. It was a lot more work than we initially had planned. In the end, we did not do the interspersed plan and act, but but it was an idea. Also, it requires an extensive design. And the other aspect was using fake components. So we developed a lot of fake components so we could run integration tests without having dependencies on other modules. And this was possible because we also had clear interface definitions. And one of the important lessons for not only us, but for most of the other teams who actually were pretty close to us, but could not, could not reach our score, was mainly because they had some issues writing down JSON files. These things actually sound pretty trivial, but turns out that this also proved to be one of the deciding factor. Other things like already Dave mentioned in the first talk. I see that we'll just rush through this. So these are the things that Dave has already talked about. So I'll just skip this. And yeah, in the end, we figured after using all this, we figured that we could have used the plugin architecture that is what MoveIt is based on, but in the end we used it the other way, as you can see. This is some timing analysis, but I think these are all probably also available in the slides later. And yeah, these are some interesting statistics. So we completed stowing in almost half the allotted time. Even during picking, we completed more than 16 picks actually. And last year there was a comment from some of the audience that the robots were moving like icebergs, but apparently we are not moving like that anymore. So thank you.
All right, thanks so much for that presentation there, Mukunda. So there was one question about your pipeline by Michael Gerner. If you actually use an existing pipeline or you built your own?
Yes, we actually did not use the existing pipeline. And when I say pipeline, it's a bit of a stretch, I would say. But what we simply did was because the existing pipeline in the MoveIt software framework, you can also create your own pipelines as well, where a pipeline itself is actually a class, but we did not use it that way. But we made our own sequence of move group API calls and move robot state API calls. So that is how I would call it. That's what we call as a pipeline.
Okay. Thanks. So now we'll go ahead and move on to the next presentation by Michael Ferguson from Fetch Robotics. Michael, are you there?
Yep. Can you hear me?
Yep, we can hear you.
Great.
Let me just bring up your presentation.
Okay.
All right. Go ahead, please.
Okay. Yeah, so this will be maybe a slightly different talk. Certainly, my background is a little bit different, coming from a little bit more of a company side, and so I'll just get right into it. Okay, so I'm going to just briefly say a little bit about Fetch Robotics so you understand sort of where some of these comments are coming from and whatnot. So we're a relatively small startup here in Silicon Valley, founded in 2014. We've grown to about 45 employees at this point. And we're big proponents of ROS and open source. So we were a platinum sponsor of ROSCon, and obviously we build robots and use ROS. So we build 2 robots, and so the picture that you see there is our 2 robots, Fetch and Freight. Fetch is the robot on the left, so that's the robot with the mobile base. It's got an arm on it, it's got a torso, it's got a head, and so certainly this is a really good candidate for MoveIt. And then the other robot is Freight, which doesn't use MoveIt but does use ROS and pieces of the navigation stack and things like that. And so both of these platforms, they use ROS. In our R&D product, we do ship Fetch using basically the fully open MoveIt with configurations built in for it and whatnot. And I guess I should actually say there, we make 2 different sort of product lines. They're also sort of the same hardware. It's really just a software aspect of the research robots going into different research labs, be it university is certainly big, but actually we've seen a lot of sort of corporate groups that are very interested in how they can use robots, how they can use ROS, and so this gives them sort of a platform to get started on that and see where they can push the boundaries and apply their different corporate knowledge to it. Okay, so I'm going to start a little bit just by talking a bit about ROS and a little bit more generically than just MoveIt, because it sort of frames the MoveIt discussion as well. Most people look at it and they think that all you need to make a robot is ROS, right? Like we've got some really great advertising. Maybe we're sort of shooting our own foot off there, and that the ROS community has done a great job of sort of getting the word out that ROS is great. It gives you a huge head start, things like that. But it's not the whole system, right? And sort of one of the defining characteristics that we look at is that, Fetch Robotics, we're building products, and the value is in sort of what the product does, but we're not building middleware, right? That's not the part that we're really capitalizing on, right? It's a lot like with the internet. A lot of the internet runs on like the Apache web server. That's kind of the middleware there. In a lot of ways, we see that sort of same thing with ROS. And to sort of understand sort of how we come and move it as well, the ROS components that we use, we're not using the whole ROS ecosystem, right? So we're clearly using things like ROS CPP and ROS Pi, the core libraries. We're using things like ActionLib because it builds sort of a more stateful system on top of base messages. And then we're using a lot of the tools that have huge value propositions for us, things like RViz and RQT, a lot of the graphical tools that we wouldn't want to have to develop in-house, but they're not actually something our customers even see. They're really more developer tools. And then the various drivers, a lot of hardware vendors have started to actually, particularly the sensor vendors, have really started to release drivers, which is pretty awesome. And then there's sort of the robot primitives, which on our research platforms are basically the baseline that's shipped out there. So we certainly, we put a lot of work right now into maintaining the navigation system. We put a little less into MoveIt. I try to be involved, but haven't found as much time as I would like to really be involved in MoveIt recently. And so it's been more of a sort of an advisory aspect. But so there's those primitives. I think one of the big things with those to understand is that they're not, in a lot of ways, they're not fully there, right? They're sort of their tools, their starting points, and they can get you pretty far, but they're not quite product ready. And so that's definitely one of the ways that we approach it. And I can see already there's a question on the side sort of asking about, so the non-R&D robots don't use MoveIt. And it's not exactly that, but we've replaced such a large portion of MoveIt that I don't consider, and the same with the navigation stack. At this point, I think all we really use is the cost map interfaces out of navigation. We've replaced every other piece of code in the system, and we've really just kept that API for ease of use when we move things back and forth between our research systems and our non-research systems. So when we approach MoveIt, obviously we're really interested in this project because it's a large community. It's even larger than just MoveIt itself, right? I can even see like some of the questions that have come up on the side during this are from people who are not maybe really involved in MoveIt, but very involved in OMPL or FCL, right? And so the community is really big, which is important to any open source project sort of staying alive. It runs on numerous platforms. It's somewhat easy to move on to new platforms. So it's tested on a lot of different things. Even if we change some of our base level system, it'll probably still work there. But the really big thing to us is that, there's a lot of pieces that are plugin based, right? And so, you've got plugin based interfaces, which have allowed us to do things like write new planners and write new planning adapters, which I'll talk a little bit about more in a second. And then one of the things for those research customers, certainly that's really the biggest things like this move group interface, this pick and place interface. They can sort of, not exactly, but very close, kind of use MoveIt as, just planning as a service or whatnot, right? Like they don't have to actually know exactly how the system's planning, but they can sort of get that out of box experience, which is actually really amazing because if you think back to when the PR2 first came out onto the market, we didn't have any of that sort of aspect, right? You had sort of navigation, and you had a very sort of hodgepodge thing that could allow you to get to move the arm around, but it wasn't this sort of like end-to-end grasping system that you could sort of deploy relatively quickly with only a few things that are missing. And so we kind of think about MoveIt not quite as middleware, but it is definitely more of a tool set. And I think the previous speaker also sort of mentioned that, of sort of using it like a tool set and then building the things that you need around it to sort of build up your application. But it's a huge head start, and that's really awesome. Okay, so how have we used sort of MoveIt at Fetch? Well, certainly we've used the amazing MoveIt Setup Assistant. If you're trying to deploy MoveIt on a robot and you're not using the Setup Assistant, you're doing it wrong. You should go check out that Setup Assistant. It saves you a lot of time. We've developed a bunch of new plugins. So I'm a big fan of sort of search-based planning, particularly when you start to get into really cluttered environments, which tend to be sort of, those densely packed shelves and whatnot that we're trying to work on in our commercial products. And so, new planners that we can sort of load in. We've developed our own collision checkers in order to speed that sort of thing up. And so those are new plugins that we've put in. And trajectory adapters, those are definitely one of the pieces that we've worked on. For us, one of the challenges with MoveIt is sort of stability, right? It's still under development. It's sort of it's a moving target, as you would expect from something called MoveIt, right? And so that does present a challenge when you're trying to use it in more of a stable product, less of a research aspect. And to sort of alleviate that, we've done a lot of building these sort of end-to-end integration tests. And so we've actually got a whole suite of tests that run basically a simulated fetch, do a whole bunch of different plans with all of the different planners that we use and things like that. And so we can very quickly get a go, no-go on whether a new release is working for us or if there's a problem. We run all of those tests in our BuildBot ROS build farm. And then we do a lot of staging of packages. So, our end customers, we don't want to see, we can break the world all we want on our side as long as we don't roll it out to the customers. And so we actually stage a copy of pretty much the whole ROS build farm with our packages built on top of it. And we test that sort of end to end before we roll it out. So not every ROS release, you sort of get those ROS releases and MoveIt releases maybe every 3 to 4 weeks get synced through. Not every one of those actually gets sent out to our end customers, but certainly a number of them. And I should actually mention here, so when I was talking about the MoveIt Setup Assistant, it's really great. It gets you a lot of the way through. One of the challenges I think we've seen with that is, if you're changing, so we have the end effector on the robot is sort of a point of integration. And so you can swap the grippers out and whatnot. And it's really easy to do on the mechanical side, and drivers are generally pretty easy to do as well. And then sort of swapping it in the planning setup and making sure that everything works. That's where the real challenge is. And so actually this picture here is a third-party gripper from Saki Robotics. And that's one that we've put on a robot recently and played a bit around with. And certainly we had an intern that actually did a whole bunch of different gripper integrations to sort of show that the mechanically and even getting the software up and running was pretty straightforward. Still some stumbling points there with sort of the way the URDF works with MoveIt, but a lot more of that's on the URDF side than on the MoveIt side even maybe. So obviously we're using MoveIt on real robots, and that presents some different challenges. I find that a large portion of the MoveIt community is actually people who are working on planning or some sub aspect of planning, be it collision checking or whatnot. They tend to run a lot of stuff in sort of simulated environments. We have these fake MoveIt motion controllers or controller manager plugins that sort of let you just fake out the robot with no physics or anything even. And that's really great for planning and sort of checking, hey, is my planning time really fast and whatnot? But it isn't everything, right? It's important, but it isn't everything. And so, things like smoothness and bounded velocity and acceleration matter a lot, because if we generate a motion plan that looks great in our viz, and then we send it to the robot, and the robot arm can't keep up, or ends up it's just not a good command for it, you might get a lot of sort of visible vibration or something like that. And so those are definitely an area that we've spent some time in. Also, in real robots, you actually have to deal with the perception aspect. You don't know where everything is in the real world, and you have to deal with sort of grasp evaluation, because you actually do care about the physics of it. Of does it actually hold on to that item as you're moving it around? And so Dave mentioned that earlier, that these are two areas that we don't have a lot of in MoveIt. We at Fetch, we've built a couple of different packages related to that. One of those is called Simple Grasping. It's actually under my personal GitHub, because it actually predates Fetch, but Fetch has worked on it a bit. And that package basically provides sort of geometric, hey, there's objects on a tabletop, pull those out, generate a grasp for them and whatnot. And in a lot of ways, it has the same functionality as that huge PR2 grasping pipeline, but without a lot of the dependencies, and with a lot more robustness, because we put quite a bit more time into it, I think. And then the other part is that Dave, I think, even alluded to this earlier. We've done quite a bit of work on sort of better smoothing, better time parameterization, because that's definitely been one of the pieces of MoveIt that didn't work really great on our robot out of the gate. In particular, we've really tuned the arm to be very velocity driven. And so if you have a motion plan that comes out that's not got improper velocities or improper acceleration, isn't bounded on the accelerations and whatnot, you don't get the sort of performance you want out of it. And so we do have that trajectory adapter. I swear it's coming. I'm hoping to have that actually sort of into pull request shortly, and then definitely merged before the end of the year, so that people can start to use that. It is something we develop sort of in-house. It does start off of some other open work and whatnot, but it's taking a little bit more time to sort of merge it the right way. So that is definitely coming, and I think that'll be very interesting to a number of people. So we are releasing pieces back at times when we see it sort of aligning with our company goals as well as the community goals. And then sort of the last thing is just talking about the sort of integration tests and whatnot. One of the pieces that we also have with that is sort of running Fetch in Gazebo with MoveIt. And so this is actually released. It's fully in Debs and Indigo. I actually, during this call, I've been working on releasing into Jade and Kinetic since I got a chance to work on that a little bit. So those are coming, but basically there's a really cool demo in here, in that you can actually fire up a Gazebo instance, you fire up a Fetch that's in there, it's all running in Debians, it's using the nav stack and MoveIt, and basically the robot drives from the starting position over on the side, drives over to that table, raises its torso, looks at the item, uses the simple grasping package to detect where that block is, reaches out, grabs the block, retracts its arm, tucks its torso, drives to the other room. You can just see a table through the doorway on the other side, and drives over there and sets the block down. And so that is really cool, as sort of a full out of the box mobile manipulation demo. If you're sort of new to MoveIt, new to ROS maybe, this is a really great thing where you can kind of run it, see all those things working out of the box, and then all of the code that's being used in that entire system is entirely open. So you can sort of dig in and see where you want to grab that and use that in your own application. And that is what I've got. So trying to help catch us up on the timeline maybe a little bit here. Thank you.
All right, excellent. That was some great stuff. Can't wait to go and try out that demo.
Thanks. I think I actually hit on all the questions that I saw go by just as they were coming up, since it was easiest to do them on the slides. So
I believe so, yes.
Yep.
All right. Well, then that's that. Thank you so much for that. And we'll, I guess, move on to the next presenter, which is a QA session with developer and founder, Dr. Ioan Sucan. Let me upload your slide. All right, Ioan. I can see you're muted, so go ahead. We're not able to hear you, Ioan. I think we're having a little bit of trouble with the audio at the moment. Oh, I see. It's a message from Dave saying his building has been having issues today. Okay, we'll just wait a few more minutes. Hopefully he gets that resolved. I can hear some noise in the background.
How about now? Can you hear me now?
I can hear you now.
Excellent. Hello, everyone. Sorry about the technical difficulties. First of all, thank you very much for all these presentations and all the work that you're doing on MoveIt. This is super awesome. Dave asked me to sort of show up and answer questions if any of my answers are still of use. And tell you, like, specifically, Dave actually gave me like a list of questions. Yeah, I don't know if you're tracking it in the chat, but well, as you may know, Willow kind of ended slightly before we were able to really produce a non-alpha product or to try and move it into a real product. And the thing that I had in mind at the time when we were working on MoveIt was really that this is going to be a framework that really is just a set of modules that exists alongside with benchmarks, and then you kind of pick the set of components and modules that you need for your particular application. Ideally, you wouldn't have to write too many of your own modules, and then again, based on benchmark results, you can build your own application. And kind of like the poster child for that application was the pick and place pipeline. I realized that that's not quite done and not as robust as it needs to be to actually be useful. And this is the thing that we were working on sort of towards the end. That was kind of like the main thing. Yeah, so I'm reading through questions now. Thank you, Michael. I'll try and answer some other questions. So Mark asked, why not kinodynamic planning integrated with MoveIt? Frankly, time constraints and efficiency. So it didn't seem that, at least at the time, for our PR2 related applications, we needed any kind of kinodynamic motion planning. The APIs were slightly different, and simply we did not have time to extend the set of features necessary to support kinodynamic planning. And since there was not a strong need for it, we just didn't do it. Other details here, again, getting back to Dave's question. In terms of coding, I just want to say that one of the things that I really wanted to get done was merging into one repository. So thank you, Dave, for leading that. Getting back to the pick and place part, in particular, we've had issues with Cartesian planning, sort of like the last little bit, like to actually pick up objects. We didn't have a grass planner. I believe this was mentioned earlier in the meeting. I think actually the grass planner we have is kind of like a placeholder that Dave wrote a while ago. And I don't think we have anything better right now. So, yeah. And again, related to this, and this was also mentioned, like with like the question on RRT and KPs. Effectively, figuring out the settings that you need for a planner is a complicated business, and it really depends on the type of problems you're trying to solve. And of course, I'm biased for KPs, but one of the inputs for this planner is a projection that effectively guides the search for that planner. And I believe the default right now is just using the first two angles of the joints of an arm. That is chosen simply because it's cheap to compute, but it's not necessarily the most effective projection. Typically, the behavior of a KP-like planner with a poor projection is producing paths that are super long, and it produces them slower than other planners. On the other hand, if you do have a good projection, perhaps one that's more expensive to compute, I don't know, depending on your problem, Cartesian projections type of stuff would work better, perhaps. That may lead to significantly better results. But of course, this needs to be backed up by benchmarks and your particular applications. You can't say that one particular planner is better than others. Okay, so Dave asks what I've learned at X that I would like to share. I'm sorry, I cannot share anything. I'm kidding. I think I have really learned that 80% of the work is in getting the last 20% done, like for real. And I think you can take that to the next level and say like 90% of the work is getting the last 10%. In terms of specific details, use new coding standards. I would strongly endorse C++, 11, 14. I think that taking advantage of language features would make for simpler code. And any other questions? Feel free to interrupt. Okay, well, since there's no more questions and we're already 15 minutes over time, I would like to again thank you. I
think there's one more question from Dave.
Yes, so design decisions. Dave, you need to clarify that. Like, what do you mean by design decisions? Or like, I mean, that's a...
Yourself, Dave.
I'm sorry?
I was telling Dave to unmute himself if he wanted to elaborate more on that.
So the only thing that I mean, if I understand your question correctly, Dave, this really is based on the fact that depending on your problem, you don't know exactly what set of things is going to work the best. And because of that, you need effectively a modular framework and benchmarks, in my mind. And that is effectively what motivated this design. So what do you mean by moving to a monolithic architecture? I don't... why do you believe MoveIt is a monolithic architecture? Oh, simply because it's one node. I think you can actually achieve better efficiency And well, actually, the main node is move group. So no, it's not one node, but you can run most of your stuff in one node. And I think you can get better efficiency with that in general. And effectively, if you want to deliver a solution as a product to a user, then you don't want to have, I don't know, 3n plus k subsystems that each need to run individually. You can actually just build one thing and tell them, okay, this is the one executable, this is the one library. We thought about nodelets, but again, resources in terms of time.
Okay, I think that does it for questions, and thank you so much for answering those questions, Ian. It was
Of course, my pleasure. Thank you for doing all the work.
No problem. All right, well, with that, we wrap up the meeting. Thank you everyone for attending and for staying a few extra minutes past the time that we said we were gonna spend on this. I think it was all worth it. And we look forward to the next meeting. And all of this, the slides and the video, the recorded video of this presentation will be available online pretty soon. So just keep an eye open for that. Thank you.